Good afternoon, everybody. Today's speaker is Giorgio Stefani, and his talk is about, the title of his talk is on the monotonicity of perimeter of nested convex sets.
So first of all, thanks to the organizers for this opportunity. It's very nice to be here at the AJS seminar. So as you can see, I hope you can see also from home, is so the title of my talk is something connecting to the monotonicity of perimeter. So my talk will be quite elementary, meaning that it is of geometrical flavor with some analysis flavor, and it will be quite simple. And these notes will be put on my website. If you spot some errors, misprints, tell me that I will correct them. And this is, let's see if the pointer works. Yes, this is a collaboration. So it's some works in collaboration with Konstantinos Bessas, now postdoc in Pavia, Flavia Giannetti, professor in Naples, and Giorgio Saracco, now at TDB in Florence. So monotonicity. So my setting, I will be in a RAM. And I will consider dimension bigger or equal than 2. And for me, the interest is on convex bodies. What is a convex body? So of course it's a convex set, but it's a body. So it's a compact set, and I will always assume that the set will have non-empty interior. What does it mean? So for example, if your set is containing half, say in an hyperplane of a dimension n-1 convex, that is a convex set. It is compact, but it is not a convex body because the interior is empty. Okay, so I want them to be flat, essentially. There is something that you have to know, but you can just say, okay, it's like that. That is, for any convex body, the perimeter, so the area surface of the boundary, is nothing but essentially the Hausdorff n-1 dimensional measure. So we are in dimension n, so the surface area will be of dimension n-1 of the topological boundary. So I don't care about the regularity of the topological boundary, whatever. You just take it as essentially it is like that. We don't care about formalities. If you are not familiar with that, then imagine simply it is just the surface area of the boundary. Now, the theorem that I want to talk about is this one. This theorem is known since, I would say, ancient Greek. And Archimedes, in his work on the sphere and the cylinder, took it as a postulate at the starting part of the book. And the theorem is the following one. So if you have two convex bodies, A and B, A inside B, so it's two potatoes, this one, the perimeter of the inner set is always less or equal than the perimeter of the larger set, which is quite intuitive, meaning that you just draw the picture and that's it. And this was essentially the proof by the ancient Greek. Now, I will try to give you at least a sketch of the proof to understand why it is true. There are many possible proofs. I will show you just one. So the idea is to start with this claim, that is, if you give me a closed half space, okay, H, and a convex body E, then I take the intersection of E and this H, and what I want to say is that the perimeter of the sliced potato is less or equal than the perimeter of the original potato. Okay, so blue part is the sliced potato, and the red part is the original potato, and so the half space is in this part. Okay. Now, how to prove that? So let's try to prove this basic case, okay? H is an half space, so after translation I can move everything centered in the origin. And so I have a direction, which is, I can take the inner unit normal to the boundary. So it's this unitary vector here, pointing in the inside of the half space. And then I take a constant vector field, X. And X will be a vector field which is constantly equal to minus this direction. Easy. This vector field is as smooth as we want, it's constant. So the divergence of this vector will be 0 whenever I take it. So I will integrate the divergence of this vector field in the bit of potato that is left out. So divergence theorem, this is probably the most advanced thing I will use in this presentation. So the divergence theorems tell you that you have to integrate your vector field up to a sign. So I'm choosing the inner unit normal here of this thing, and on the boundary of this left part of the potato, a right part of the potato. Okay. So the boundary of what is here is made of two things. One is the part of the boundary of E intersected with the complement of the half space, and the part of the boundary of the half space which is inside the potato, inside E. And you can simply draw, so simply understand from the picture that when you are looking to the normal on the boundary of E, you get the normal of E. Okay, the inner unit normal, and once you're looking the normal here, then you get the opposite normal of the half space. Okay. So point is that if you plug these pieces of information inside, what you get is that on the part of the boundary of E, you get this new E, while on the part of the boundary of H, you get mu H. But X was constantly minus mu H, so this is -1, okay? And so you are integrating -1 with respect to the Hausdorff n-1 dimensional measure, and so you get this thing here. Measure area surface of this part. This part here is very easy, no? Because I have something, which is the scalar product of two unitary vectors. So scalar product is less or equal than 1. So I put the modulus here and give this bound easily. So it's the measure, surface area measure, of the part of the boundary inside the complement of H. So what we get all in all in this equation, so inequality 1, which is telling you that you can exchange H and E, and you are growing up. Okay. So I go back. So I look to my perimeter, initial perimeter of E intersected with H. And what is that? Well, it is the Hausdorff measure of the boundary, as we said. The boundary of this thing is made of two parts. The part of the boundary of E, which is inside H, and the boundary of H, which is inside E. Okay? And then, okay, this is a union, so this is a measure, so monotonicity of this measure, so I get these two pieces. The second one is the thing that I want to control using the piece of information that I have before. And point is that this can be bounded with this, okay, as we said before. And now I have the measure of the surface of, say, of the boundary of E inside H, and the measure of the boundary of E inside H complement. So apart from very particular situation which you can work out, this is the full measure of the boundary of E, okay? And so this is perimeter of E. And this proves our initial claim, okay? This was our claim. So if you slice a potato, okay, the sliced potato has less surface area, easy. And now we pass to the general case of two potatoes, one beside the other. So to prove that, we recall this elementary fact, which you can easily imagine. So if you are given a convex body, there exists a sequence of closed half spaces realizing the convex body that you are given as an intersection. This is easy to believe if your set A is, say, a polyhedral set. As you will imagine, you will take, say, the half spaces on the boundary, okay, giving you the boundary, and then you get what you get, no? If it is not polyhedral, then you do it by approximation. I mean, you approximate your convex body by a polyhedral set, you approximate that with half spaces, and then you pass to the limit this approximation. Now, A is contained in B, So A is the intersection of A and B, topologically speaking. And we have said that A is the intersection of this infinite number of half spaces. So the perimeter of A is the perimeter of this thing here. Now, I can say that in a good way, this set here, this infinite intersection, is the limit of finite intersection, okay? Finite number of intersection, n. And now I say, okay, this set here is converging very well to this set here, at least L1, okay? And so by elementary property of the perimeter, lower semi-continuity property, I can put the limit outside as a limit, okay? And I get this here. So I have to estimate the perimeter of B intersected with a finite number of closed half spaces. But I can remove one half space by one in n iterations, no? Because I have at least n big N half spaces intersected. And so I can use my claim n times to get that this perimeter here is less or equal than the perimeter of B. But then who cares about the limit, because n has disappeared, and then we get the proof. Okay? So we prove that the perimeter of A is less or equal than the perimeter of B. This is not the proof that was written in Archimedes' book, because it was taken as a postulate, but the argument that he uses in 2-dimension, 3-dimension, is morally the same. That is, he was able to understand that cutting an object with these operations, the intersection with the half space, which was half plane or really half space, was decreasing the surface area, which was quite remarkable, I mean, for this time. And so now I would say, okay, why do we care about this monotonicity? Well, there is an application which for me is fun, and it is an estimation, a lower bound on the convex component of the number of convex components of a set. So now I will give you a set E as before, so a potato, but I'm not assuming that it is convex, okay? It is just a compact set, say with non-empty interior, so it's not degenerate, okay? Always in dimension 2. So now I want to decompose my compact set in this way. It is the union of convex bodies such that they do not overlap. That is, the measure of the overlapping part is 0. Essentially, they are touching with the boundaries. This is what I want. Okay. This is an example. So I have this set E, which is this U shape, okay? And I would like to understand in which way I can divide it into convex sets. Well, you immediately realize that you have at least to use 3 convex sets. One has to be something like that, one has to be by similarity something like that, and one has to take this part into consideration. Of course, this decomposition is not unique. This is one possible decomposition, but you can say consider the one which is flat here, for example. And this is just the minimal number that you need to have, because, for example, you can split this component here in twice, you get 4 connected components, but I mean, you can use just 3. And why do you need 3 convex components? Because you have angles, no? You have this point here and this point here cannot be in the same convex component, because the line connecting them is going outside. So if they were in the same convex component, the line will be inside E. And the same story applies here by symmetry, no? So this proves that the minimal number of convex components of this set is 3. Now, assume that you're given this compact set, non-degenerate, and assume that you have such decomposition. So you can split it in convex sets. Now, question is, what is the minimal number of convex components that you need? This K mean. Now, first thing one realizes that I have never said that your set is connected. Maybe it was just 2 potatoes, okay? Well, if you have 2 potatoes, it means that it has 2 connected components. So it means that the minimal number we are looking for is at least the number of connecting components, because if you are convex, then you are connected. This is very easy to see. So for simplicity, one can assume that I'm given a potato which is not convex, compact set, but which is connected at least. And say with the non-empty interior, say it is not degenerate. Now, convex hull. So what I will use below will be the convex hull of my non-convex potato. What is a convex hull? Well, it is easy to imagine. You have this non-convex set, and you will convexify it in this way. So you will consider all the possible convex combination of 2 points inside this set E. This will be the convex hull. So essentially, it's saying that if you have a U shape, then you will connect the U shape in such a way that you fill this hole here. Okay. So elementarily, E is already contained in its convex hull, and the convex hull is a convex body. It's not easy. It is easy to see that if you give me a compact set, then the convex hull has to be compact as well. Okay, this can be easily seen. Now, as I said, you have a non-convex with non-empty interior. Yeah, sure. Because otherwise, I mean, of course, I am assuming that I have this decomposition. So this is my assumption. So by this assumption, I have non-empty interior because each EI will have non-empty interior, and so my set will have. So I won't consider degenerate situations. Or if it is degenerate, then I go one dimension less. So I have one possible decomposition. Now, the perimeter of my set E has to be, as I said...
Wait, I have a question.
Yeah, sure.
Convex hull is the smallest convex set that contains E, right?
Yes.
So I think that it is wrong, the description, because if you take 3 points that are not on a line, this description, a bit up, describes the boundary of a triangle.
Ah, yeah, you're right. Sure. There is a missing part here.
You have to reiterate this procedure.
Yeah, you have to iterate. Yeah, sure. This was just to give the idea. This is not correct. You're right, because he said if you have 3 points and then you consider this, then you immediately get this, but you don't have this inside interior part here. Yeah, you're right. This is a misprint. So
the initial set is connected. This cannot happen.
Yeah. So the point is that we are considering something which is bound. Say one has to be careful because I mean, there is also a connection assumption. So I have to rewrite this in a more formal way, but this was just to give the idea, okay? But you are right, you are completely right. Thank you very much. What was something? Okay. Yeah. So going back. So going back. So I have my perimeter. So the perimeter will be, as we said, the measure of the boundary of my set E. My set E is decomposed in this way, okay? But the boundary of this union is for sure contained in the union of the boundaries, okay? I will count, now I'm counting things twice, no? Because if I have two connected convex components here, then this part of the boundary will be counted twice, okay? Then the outward measure is the measure, so I use, say, this is less or equal than the sum of the measures, and this is the perimeter of each EI. Now, I go back and recall that EI is contained in E, and E is contained in the convex hull of E. So these two convex bodies are nested. So EI is in convex hull. And so this is by monotonicity of the perimeter of EI is less or equal than the perimeter of the convex hull of E. And this does not depend on I. So I have K times the perimeter of the convex hull. But this was the case for any such decomposition. So K is always bigger than this ratio. And in particular, it is the minimal number that I can put there. And so if I take the upper integer part of this fraction, this can be a number with comma something, I will take the upper integer part of this fraction, then I get this bottom. Oh, sorry. I killed K. Okay. Now, this was proved, this was observed in a paper by Giannetti and G in 2008. Now I will go a little bit far and I will consider quantitative monotonicity. So again, I have two convex bodies. It's not necessary here that for the definition that you need convexity, you just can do that for compact sets. I will consider the Hausdorff distance. So if you don't know what Hausdorff distance is, it is like that. So you will look for points doing this. You minimize, take a point B in B and a point A in A, and you minimize with respect to the point A in A, and then you take, this is something, so a minimum, which is a function of B, and then take the maximum of this function with respect to the point B. So here is the picture. So again, the two potatoes, one inside the other. So I have the Hausdorff distance, which is the distance between these 2 points here, we call A and B. Of course, this is a sub-info by definition, but it is a max and a mean because they are compact. So everything is continuous, so you get minimizer, maximizer, okay, AB. B will be generically a point in B which is not in A, and A, by definition, will be, one can prove that from this definition, that will be the projection, the orthogonal projection of the point B onto the convex set A. And in fact, if you take this line here, connecting A and B, and then you take the orthogonal plane to this line, this will be a supporting hyperplane for the set P, which means that it is essentially the tangent plane. It doesn't have to be, say, really the tangent one, because in convex set you can have corners, okay? But the point is that it will put the set A on the left in this picture, so on this part here. So there is no A in this part of the picture. So from now on, H will always be the outer distance between A and B. And H, you can write it down simply saying, okay, I know A, I know B, then H will be this half space here.
I'm sorry,
yeah.
You always assuming A contains B? Because otherwise you have to symmetrize the
Sure. A will be always in B. I mean, yeah, notation. But A will always be in B. Okay. Theorem. So this was proved for the first time by Carrozza, Giannetti, Leonetti, and Passarelli di Napoli in two papers. The first one, 2015, the second one, 2016. First one was in dimension 2 on the plane. So I'm interested in the difference between the perimeter of B minus the perimeter of A. And this is important that A is contained in B, because I want this to be non-negative. Okay, so I will denote by delta AB the difference between perimeter of B minus perimeter of A. This difference can be estimated. It's not just bigger or equal than 0. It's bigger than something that depends on the figure that I've shown you before. You have this fraction here, where H is the Hausdorff distance, and here you put something which is measuring the interfaces between, say, the two sets. That is, what is the area, in this case the length, because you're in dimension 2, of this section of P. Okay, so I will be interested in how much surface I have here, and this is in one dimension. It is essentially the length, because in one dimension you will have this line here. Okay, so we have this lower bound. 1 year later, they were able to generalize it to dimension 3 in this way. So you have a similarly looking fraction, but where now you find a different constant. First it was 2, then it was pi, and you find a different parameter here appearing D. D is the distance between the point A and the curve. Now we are in dimension 3. So what is the correct picture? That is here, you take this curve, gamma, which is the boundary of B intersected with the boundary of H. Okay. And you take the minimal, so the distance between the point A and this curve, gamma. It can be 0. Okay, generically speaking. Now, these results were presented in Levico Terme some years ago, and by chance I was sitting at the same table with Francesco Leonetti and Benita Carrozza, and I asked, okay, what about NB 3,4? And they said, well, if you go in higher dimension, this trick with the parameterization of the curve doesn't work, because then you will have a surface there. Because in 3 dimensions it is a curve. In 4 dimensions it is a surface. So it's very hard to understand via parameterization. So it requires a different strategy. So what I was able to prove some years after that, it was this. That is, whatever dimension you give me, you will be able to lower bound the difference with this fraction. So here, omega n minus 1 is the volume of the n minus 1 dimensional ball. Okay, it's a disk, actually, if you see in dimension, if you see it in dimension n. And then you have this parameter, which is a radius. H will always be the out of distance, as I said. The radius is given in this way. So I will take the area, so n minus 1 dimensional surface of B in sliced with this H. Okay, I will take the intersection between this bound, this H, the boundary of H, with B. I will measure this area surface, which has dimension n minus 1, so it is an area surface. And I will take the radius that I need to put this area as a disk. Okay, this is the definition of R. This is the mean radius, essentially. And if you go back to dimension 3, what you get is that this mean radius is always less or equal than the distance from the point A to the boundary. And this implies, once you study a little bit this function here with respect to R, as well as this function here with respect to D, that this will improve the result in dimension 3. And this inequality is usually strict. Okay. Sketch of proof, we'll try. Again, 2 potatoes, the composition as usual, H, A, and B, already everything set. What I want to emphasize is this set E, which is the intersection, so the sliced potato, as usual. I will add a new actor in this talk, which is this cone here. So I will draw the cone from with vertex P and base this intersection here. So it's something that is n-dimensional and it is convex. And from the picture, you can see that A is inside this part of B, so which I call E, and E is, of course, inside this new convex body, the union of E with this cone, and this union is inside B. So by monotonicity, the perimeter of B is larger than the perimeter of this union, and the perimeter of A is smaller than the perimeter of E. So here I apply monotonicity 2 times. Okay. But now, what is the perimeter of E union with C? Well, easy. So I have to estimate the perimeter of this stuff here. So I have this perimeter, which is the perimeter of B inside H. Okay. And then I have this part here, which is the lateral surface of my cone. The perimeter of E is the same part, as we have seen, plus the part which is the base of the cone. Then this difference is bounded from below by this difference here. So it's just something depending on the cone. Now, the base of the cone is somewhat assigned because I am given the set B, so I am given this particular slice because I am also given A. So I have somehow fixed the position of this point here. So this slice will be given. So the area of this slice will be given. So this number here is given, and we will call it in this way. This is the definition of R. So what I want to know is if I can put something below here. And this something amounts to minimize essentially this thing here, putting as constraint the height of my cone, which is fixed, is given by the problem, and the area of the base of my cone. Now, the idea is that among all cones with the same height and given base area, the minimal area that you can do for the lateral part is the one given by the right round cone. So you have to take a straight cone, so 90 degrees here, with a circle. This is a very simple principle. I won't enter into details, but this is part of the Schwartz symmetrization. So essentially, you replace each slice of your set with a corresponding slice, which is a round disk of the same size, the same area. And this will arrange it in this round cone. And so once you compute, so you have the height, you have the base radius, then you can compute essentially this length here, and by Pythagoras, and then you can recall that it is something which is rotating in dimension n, and then you do some integral computation, and you're done. So that's a matter of computation. Now, if you go back to the application that I've shown you on the minimal number of convex components, you can actually exploit this, because you have a piece of information more. In dimension 2, it was already done by Carrozza and friends, but in dimension bigger than 2, it was not done, and we did it with Flavia. And the place in which you can exploit that, I will go back, and this is something that you cannot do with a blackboard, but it's here, no? Here I have used monotonicity. Here I can put something more. So I can put a more precise inequality depending on where this component is located with respect to the convex arc. So if I know that my strange set E has sufficiently number of, let's say, turnaround, so L shapes or U shapes, then I can say something concerning this additional piece that I can put there. And so I get a better lower bound that will improve this strictly in any dimension. So I won't show this application, but you can imagine that. Now, question is, one of the questions of the abstract was, are there other perimeters with this property? So this is always about Euclidean perimeter. So one natural question would be, okay, let's charge each particle a little bit. So instead of measuring just the boundary of E, I will consider a weighted perimeter. That is, on each point, I will put a weight, which is this function f, which I will assume that it is C1, even C infinity, we don't care. I mean, this is done without loss of generality in the end. And so I ask, okay, let's look to this perimeter, at this perimeter. Does it satisfy the monotonicity? I would say everybody is going to say no. Because if f is non-constant, then something is going to happen. I can put some slides, I mean, some boundary on the place where f is locally minimum, achieves local minimum, and another part of the boundary, which is where the function f is slightly bigger. This is essentially the intuitive idea, but with Giorgio Saracco, actually, we were not able to do that for a long time, because it requires a little bit of, tricky things. But the point is that, yeah, this is a rigidity result, meaning that this perimeter here is monotone if and only if the function is constant, possibly zero. And why we are not able to do that? Because actually we were tackling the more general problem of saying, assume that your function depends also on the normal to the boundary. So I will add something which is, so here I will consider something which is of this shape here. So I will add this dependence with the normal. The point is that the theorem is false in that case. And we have a counterexample which is quite stupid, but is there. You take f of this shape, okay? F is, big F is any function, the one that you like the most, C1, C infinity as you prefer, with constant divergence, non-zero. And you take a parameter B, which is larger than this function F. You can take that very sinus to sinus, whatever you prefer. And you immediately realize that the perimeter PF, which is defined in this way, is something which is the sum of the perimeter of E times alpha plus the perimeter, the volume of E times beta. And that is, of course, monotone, because the volume is always monotone, and the perimeter, Euclidean perimeter, it is, as we have shown. So the question is, okay, we don't know what happens in this more general case. So how to prove that? Well, the sketch of the proof is essentially formalizing the idea that I told you before. So let's fix two potatoes. One potato is very nice, it's a cube. Okay, this is cube in n dimension, with a facet, the upper one in direction xn, which is centered at the origin. Okay, so very, very centered construction. And I will put a bump over this facet, which can be realized, say, just to keep it simple, as the graph of a function over this facet here. So it's a bump, it's the graph of a convex function h, and I will delete this function h by this parameter lambda. Okay, lambda equal to 0, bigger or equal than 0. When lambda is 0, then you just get the flat thing. And I will assume that h is a convex function which is strictly positive. So as competitors, I will take A, this cube here, and B, the full thing, that is A union this bump. Since H is convex, and this is important, you will get since H is concave, sorry, you will get a convex body. You cannot consider any graph. You just need some concavity to ensure convexity. So we are assuming monotonicity. In particular, the perimeter will be monotone on this couple, B and A. And if you do the computations, essentially you have to ignore this part below, because it's common to the two sets, as we have done before. Essentially, you have this cube plus this part here, so the difference will be between the two will be these two. So the curved part will be given by the area of the graph of the function lambda h, okay, minus the part which is depending on A, which was the area of the face, okay, which is connected with the fact that you take lambda equal to 0 in that case. Now this function here, this thing here is a function of lambda and is always non-negative. So it means that if you consider that thing here, which I call phi, this function here is something that depends on lambda. Of course, I am integrating off the facet, which is so the cube was of size delta, and so this is something which is n-1 dimensional. And this function here is always say the zero value of this function is precisely that thing. So it means that at lambda equal to 0, you have a minimum. So you differentiate in 0, you get 0 because it's the minimum, and you get this piece of information. Now, assume that you divide by the volume, the n-1 dimensional volume of this cube, of this domain, and pass to the limit as delta goes to 0. Then what you get is this derivative here, everything is very small, so f is at least C1. This derivative here computed as 0 times h in 0. But in our framework, h was strictly positive in the interior. So this means that the derivative of f with respect to direction n, xn, is 0, in 0. But I have done the construction in direction xn. I can repeat it in any direction. So the derivative with respect to any direction in 0 is 0. But I centered the construction at 0. I can center it at any point. Doesn't matter, because I can take the convex set wherever I want. And so the gradient is 0 at any point. So the function has to be constant. This is what I wanted to say concerning that. In the remaining time, we'll say something about a more exotic example of perimeter, which is the non-local perimeter. The non-local perimeter is defined this way. So you give me a function, k, just measurable, non-negative, okay? And I will use that as a kernel. This is why I call it k. What is the definition of perimeter depending on this kernel? Well, you take this double integral here, and what you check is essentially the average with respect to this kernel of the difference between the characteristic of the set at a point and the characteristic of the set at another point. This is a diffuse perimeter, meaning that it depends not only on the points which are inside the set, but also on the points which are outside the set, and even very far away, for example, in the case in which this kernel is not compactly supported. A notable example is the fractional kernel, that is, you take 1 over modulus to the power n plus s, where s is a number between 0 and 1, up to a renormalization constant. And this is the example of the S fractional perimeter, which was introduced by Caffarelli, Roccojoff, and Savin 2010. Point is that question. Is this perimeter, this is some kind of perimeter function because it is considering the interaction between being in the set or not. So it is something connecting to the boundary of the set. So the idea is it's a weighted perimeter, but in a non-local sense. So question is this perimeter monotone? So the first result that I am aware of concerning this property is hidden in a paper by, a very celebrated paper by the 2Fs and 3Ms, Figalli, Fusco, Maggi, Millo, Morini, 2015, where they studied the quantitative isoperimetric property of the ball for the fractional perimeter. And we were able to generalize this to more general kernel with Konstantinos and even to more general kernel with Flavia in a recent work. Actually, it has been published, this work, some days ago. And the two assumptions that we need here are very simple. First one is the kernel has to be symmetric. So I don't care about, say, being non-invariant with reflection or something like that. So I will assume that it's symmetric. In this sense, this is not very relevant, because if you give me a kernel, then I can do every computation for the symmetrized kernel, okay? So we'll take this new kernel and do all the computations for that kernel, and it will essentially be the same. So this is not a real assumption, actually something that you can always assume. The important assumption is this thing here. So I've said this is a perimeter, but if I put, say, the ball, so I consider the perimeter of the ball, so E is a ball. Do we know that this thing is finite? It's for sure negative, but is it finite? Well, in general, no. It depends on really on this kernel here. You have to assume something, and what you need to assume is this. So the minimum with respect to, say, between 1 and modulus of h times the kernel. So you assume some integrability assumption for the kernel. Sorry, on Rn is finite. And in this situation, as soon as you give me a potato with a finite perimeter in the usual sense, then also this function is finite, is finite. So this is something that we need to know, also because we want to compute the perimeter of potatoes. So if it is not finite on potatoes, then it's not a question. And this is the being not too singular, MTS. And so, theorem, this perimeter, this strange non-local perimeter, is monotone. Actually, in a quantitative sense, I won't enter into the details, but if you assume a little bit more on the kernel K concerning its symmetry properties, so you reinforce a little bit this assumption here, which is morally always for free, which means that, for example, you take the fractional kernel, this is one possible application of that, then you get even a quantitative estimate, so you can put something here. You can add something depending on the out-of distance between the two things. And this is contained in my work with Flavia. Anyway, I won't enter into the quantitative thing because it's a little bit cumbersome. I will just give you a sketch of the proof. Yeah, I can. Sketch of the proof of this monotonicity and see what is the difference here. So the idea is the same. So as you were able to approximate potatoes with hull spaces, you always approximate potatoes with hull spaces, even here, because this perimeter, and this you can check, is lower semi-continuous, not because of something very deep. You can apply for 2 lemma, because this is non-negative, so you pass through the limit. Just need pointwise convergence, more or less. Okay, so we can just prove the monotonicity property a la Archimedes, slicing potatoes. So what do we have to do? First is to observe that thanks to the symmetry property, the perimeter is nothing but this. Considering the kernel on interactions, so for interaction between the set and what is outside the set. Okay, and this is simply because here you have 2 characteristic functions. So this thing here is either 1 or either 0, and it depends on where you are, inside or outside. Okay, and then we go on. So we take potatoes minus sliced potato, and we use this definition here. Okay, so here it is, and since we have E intersected with H, here it is the other part. And now we have to open a little bit the situation. That is, I will split this integral into parts. So the part where you are inside H and E, and the part of E which is outside H. Okay, I have just split it. And also I will split this integral here in 2 parts. So if you remember the Morgan law, which usually I don't, this is the situation, okay? And so if you split it, you can split as a piece on E complement and the piece of E complement minus, H complement minus E complement, and which is, again, by always forgetting the Morgan law, E minus H. Now I look to what I have done, and I see that there are 2 pieces in common, no? Because this thing here and this thing here are met with this thing wrong. This thing here and this thing here is the same as this thing here and this thing here. So I can cancel them, and what I am left with is this expression here, okay? So now I have to draw on a picture. Point E is always a potato, so we'll be inside a round potato. So PR for some r positive. Depends on the fact that it's simply bounded. And I will consider F as the union of my potato with the hull space. So this is the picture. So I have my potato, original one, then the ball around it, covering it, whatever it is. It's important that it's just inside. And then I have fixed this slice in hull space. And as a new set, I will consider this red set, so the union of the ball and the hull space. So let's look to the picture. First, E is contained in F. Here. The part of E outside H coincide with the part of F outside H. And precisely is this part here. Right? Then I have this other piece of information. F intersected with H is H. Sure, it is. And last but not least, and this is important, the part of F which is not in the ball is the same as the part of H, which is not the ball. And this is the story, no? Because if you remove F from the ball, you get this thing here, which is the same as removing the hull space. So sorry, if you remove the ball from F, then you get the same thing by removing the ball from H. So I go back to this mysterious thing, and I plug these informations here. Here there is a mistake. Here it is. So this is what is something that I want to show you. So first integral is with plus sign. So E is contained in F. So it means that the complement of E is bigger than the complement of F. Good. E minus H, well, E minus H is the same of F minus H. So here I've done nothing. Here I have E intersected with H, but E is inside F. So E intersected with H is the same as F intersected with H. And this is actually H because of this in here. And now if you do a little bit of computation, you realize that this set here, this new piece here, is precisely this difference. And this difference is given by the localized perimeter function. So first I've shown you the perimeter, non-local perimeter on the entire space. Now I want to localize it to a set. And it is essentially doing this. So the new set A is the new box. So I will consider interaction between A and its complement. But also I'm interested in interaction with A and its complement, even if I go outside the box. So same story here, but also considering the interaction which happens close to the boundary of H. The only interaction we don't care is what's happening outside H. So there is no interaction between A and E complement outside, both outside H. Both outside E. A. This is the K perimeter of E inside the new box A. Theorem. This was proved almost at the same time, I would say, by Valerio Pagliari in a work 2012, and also by Cabret in a paper same time. And it is quite easy to understand, but not so easy to prove. All spaces are minimal with respect to this localized perimeter. That is, if you look your non-local perimeter inside the ball of your set is doing something strange, whatever set you take. Then, if you want to minimize that part there, you have to be a half space. Okay? You have to be flat there. This is what precisely it's written here. Whatever you do, the best thing you can do to minimize this localized perimeter is to be a half space. This is the local minimality of the half spaces. The important thing is that outside the ball, you are doing the same thing. So essentially, I'm putting a boundary constraint. And now, this was the difficult phase. This was why we did all this computation, because we were able to reduce our problem to a localized problem. So here I have the localized and local perimeter to some ball. And since I know that outside the ball, I'm doing exactly the thing that the half space is doing by local minimality, this is non-zero. But if this is non-zero, then this is greater or equal than zero. And so if this is greater or equal than zero, then we are done. Now, time is over, so I will give you some questions. So dark thing here is slightly in the middle, so we put there, okay? Question, first one. As I said, we know that the perimeter, the weighted perimeter is monotone in this case. If F is constant, if and only if F is constant, if F depends just on the position X. Now, if you look to my paper with Giorgio, actually we have another case in which we were able to prove something, and the case is this one. So if F is given by the product of two functions, one is depending just on X, and it is radial, okay? It depends actually on the modulus of X. And the function, depending on the direction, is convex and one homogeneous, if you want to see as a function on Rn, then you prove that the perimeter is monotone, the weighted perimeter with respect to this particular weight is monotone if and only if the function G is constant. So you don't have dependence on the position. This generalizes the result which is known for Wolf perimeters, essentially. Okay, so in Wolf perimeter, you have just this function phi, and the weighted perimeter is usually called the Wolf perimeter. It is motivated by something happening for crystals. Question? So I will be happy to see if there is some kind of condition on the function, more general condition on the weight function to ensure or to disprove monotonicity in general. Something that for the moment we don't know. And then if you like non-local perimeter more, then I give you a different way of measuring perimeter in a non-local sense. In this case, we don't care about interaction outside, inside, and blah, blah. We just fatten the boundary. So we take the boundary of our potato and we fat it a little bit by a size r. So essentially, you take a ball of radius r and you move along it on the boundary, and you take this thing here. This thing here now is with interior non-empty, so it's something which is n-dimensional. I will take its volume. This is a rewriting of what I said and drew, that is the Minkowski sum of these two sets here. And then you divide it by what is the fattening, that is 2r, which is precisely the size of this fattening. This is so called the Minkowski perimeter, and it's quite useful because it somehow represents, say, something which is close to the usual perimeter, but it's an approximation from a volume point of view. Question, is this perimeter monotone with respect to convex, nested convex bodies? For some art, depending maybe on the convex bodies, I don't know. Second question. So with that, I thank you for your attention, also for the kind invitation again, and thank you.
Is there a question? Also from home, of course.
I have one.
Yeah, sure.
So is the last question?
Yeah.
What about do you think can we prove that this monotone is this kind of perimeter, some monotone on smaller class convex bodies?
It means, what do you mean by class?
Like zonoids. Because
or something with this polyhedral boundary.
Yeah.
Maybe. I didn't think about that. Possibly, why not? I would start with polyhedral boundary, let's say, seems reasonable. But then, I mean, because inclusion is something which is trickier here, because you can be included in this way, no? So if you fatten this, then you get something which is overlapping with the fattening of the other set. So it's not clear.
No, but maybe the first one, the question one.
I mean, these are two different questions, eh? So these two perimeters are different.
Yeah. So.
But you were asking for this thing here.
Yeah, I was thinking to that one, but maybe also the.
Okay.
I don't know. It's a question which is suitable for both.
Yeah. I mean, we tried a little bit for this general case here with Giorgio, but we were not able to do that even for say the interaction. But maybe because we were not so clever. Actually, Giorgio came here for a week, and in that week we had at least, I believe, 5 or 6 proofs that in this case you cannot be monotone. At least you have to drop the dependence here, and they were wrong every time we proved that, and the next day we were wrong. So it was a nice try. And in fact, I mean, we have a counterexample in the general case. The question is, can you classify them?
Yeah, but okay.
So that is a thing that you have to be careful, because there are counterexamples.
Yeah,
question
in the second part, you know,
no, this is completely open for me. So in this,
yeah, also it's not easy.
Yeah, I mean, maybe it can be easily disproved. I haven't think about that, but this is another instance of non-local perimeter that is quite a la mode, let's say, and for two triangles, maybe. I mean, but you have to be inside.
Sì.
Okay.
Il lato piccolo dentro e uno sottile ma lungo. Poi sono stile base.
So you say
La differenza dipende dall'angolo per il raggio.
Doing something like that. No, but they want to disprove the monotonicity.
Sì.
So in this way, I believe that the monotonicity is true, because if one is very small and the other one is very big, I mean, will be true. No, I would like to be monotone with respect. So my question is, so take this definition here, okay? So this new definition, I'm asking, is it true that if, I will write with normal, if A is a convex set which is in B, which is a convex set in Rn, you have a parameter R which is positive, then the perimeter, the weighted perimeter, let's call it perimeter M. It's a different kind of perimeter, Minkowski perimeter. Perimeter Minkowski way has this property. This I mean by being monotone. So if you think of a picture, it means that I'm giving you two potatoes. One is this thing here, one is this thing here. Okay, is A and B, and you have to fatten A little bit of R, and you have to fatten B. Okay, so here I'm fattening of size to R essentially, considering this tubular neighborhood, and then I measure the volume of blue and B and divide it by 2R, renormalize. So is that true that you get monotonicity? The point is that if this set here is very close to the boundary, then you have overlapping of the two things. And that is not so, I mean, it's not clear to me. Maybe it's obviously clear, but...
Isn't it just a consequence of the Coara formula? I mean, if you are it seems to me that the measure of the R enlargement is just the integral between 0 and R of the perimeter of the epsilon enlargement integrated with respect to epsilon.
In the smooth case, yes, but if you have corners...
No, it seems that is true even if it is non-smooth. The Coara formula works for an ellipsis function.
Yeah, because you're taking the distance, but be careful because I'm fattening the thing. So it's not just, so here it's rounded more or less.
Yes. Yes.
You just do that by co-area.
Yes, you do this.
Maybe, yeah, probably. That could be.
Yes, you do a co-area. At this point, then you compare the integrands. For the integrands, it's true because if you take the epsilon enlargement of A, is included in the epsilon enlargement of B, and so you can use the already known formula.
I see what you mean. Okay. So you're saying that at epsilon relargement you have this, but so
yes.
The point is that there is epsilon relargement from inside and outside, meaning that this will be more or less.
You do the in both directions, both inside and both outside.
Yeah, that's the point. So I'm fattening outside and inside.
Okay.
Otherwise,
but I think that you can. It is still true because it is the sum of the epsilon enlargement inside, the epsilon enlargement outside, and so if you have just to prove this for both, and again one can still use this trick. I think.
Probably yes. Probably using it by a Coara formula and then arguing on the level sets of this thing.
Yes.
One has to control these level sets, but I mean, possibly should be fine. I will think about that. I mean, maybe write me an email, please.
Okay. Yes, I will do.
And okay, thank you very much. Maybe kind of thinking about that. Thank you.
Other questions? Okay. When you fix in the plastic perimeter, when you fix E, the set,
yeah,
you take the limit.
You go to the Euclidean perimeter.
It's the Euclidean perimeter.
Exactly, and of course you have to assume something concerning this boundary here.
Okay.
So I mean, if your set is reasonable, so the limit has some some meaning, then this is precisely what you get. So that's why it will be interesting, because you are essentially saying that the monotonicity property is somehow stable with respect to this Minkowski perturbation of your function. Okay. One can also consider, I mean, there are many variations that you can do. That is, we are taking a Minkowski sum with respect to a ball. But you can say, why a ball? I can take any other convex body, delete it by radius r, and use that inside here. Does it change anything? But it will not converge, generally speaking, to the Euclidean perimeter. Changing this thing here possibly may affect your limit function. Okay.
Even though this slide.
Well, maybe if it's convex, fine. It's not too singular, say. Maybe yes. Maybe. Yeah, I didn't think about that, but possibly yes. Only if it's possible.
Any other question?
Other ones. And then avoiding the number of
Sure.
components.
Yeah.
If you know how sharp is.
So if the estimate is sharp,
Yeah.
okay. So point is, what do you mean by sharp?
Yeah.
So sharp is, in this context, is I have an example in which this inequality is a equality. This is trivially sharp because if you take E as a convex body, it's done. But the improvement we have, considering, say, the quantitative monotonicity, so you put here something more, is sharpening that because we have a quality in some cases where for this inequality you get strict inequality. So our is an inequality, for them it's a strict inequality. So our result is better because it will be an equality in all cases in which their inequality was an equality, but our equality cases are more. Okay. And usually in any dimension it works even for L shape. You take an L shape with this part here very close to the boundary, and this is enough to show that there will be always a strict inequality, but for us will be an equality in any dimension. So the difficult part here is also to construct examples or counterexamples.
If there is no question from home,
Yeah, I cannot see. So check.
okay. Seems like no. We can thank Giorgio for his talk.
Thank you again.